Ladies and gentlemen, I'm pleased to be here to talk about our project Carbon to Chem and in the view of the way from the fundamental research to systemic integration. But what we would like to do is develop carbon capture and utilization processes. And we are responsible, or our topic is the technology development and the upscaling in the first steps. If you would like to make the first step, everybody must be included into the business model just to share risks and chances. And this is done in cooperation with 22 partners from industry and from academia.
Thank you. I wanted to talk today about 5 challenges in decarbonizing chemical transformations, and particularly electrifying those chemical transformations. Task number 1, direct air capture. And where we're focusing our attention is trying to see how we can utilize electricity. Obviously, it needs to be low carbon intensity electricity per the points that Nicholas was making to, first of all, achieve a true net carbon reduction and to do that energy efficiently. You know, when we have CO2, how can we utilize or upgrade it? So that's the second task I wanted to talk about. And in reactive capture, we actually combine the steps of capture release and the step of upgrade. So my third thrust is actually about decarbonizing hydrocarbon oxidations. My last 2 tasks, one is about scale. We took on the challenge of scaling even before the technology was fully mature. Like, we scaled from the lab scale gram per day to about 100 kilograms per day in a lab demo. And then my last theme is about accelerating. And here, as many of you also are excited about, we're excited about whether machine learning can potentially help us move faster to discovering new materials. We've been working to develop these highly parallelized means of synthesizing libraries of nanoparticles that contain, say, 4 or 5 different elements that we're varying across an integrated circuit.
I'm going to describe to you the formate bicarbonate cycle. It's a concept that we have introduced 35 years ago. All right, so this is the cycle, which is the basic for this hydrogen storage and energy storage concept. It's taking the hydrogen that you produce by various methods, you convert it into the carrier, and then the carrier is being transported, and eventually you decompose it to release the hydrogen. What we have shown is actually the format bicarbonate cycle is the simplest one in terms of pressure and temperature you need for the release, and temperature and pressure you need for the charge. And it turns out that the nature of the carbon carrier is critical for the catalytic activity. And what we see here is the very, very stable catalytic activity. And this is a case study where 100 tons of hydrogen is produced by solar electricity, 8 hours a day, transportation of 600 tons of hydrogen every year by 2 methods, either Hydro-X or ammonia from Abu Dhabi to Tokyo or to Rotterdam.
With the vision of sustainable, affordable, secure energy for all, first of all, to really make an impact, we do need to have all the expertise together. And all of these are very important. For today's purpose is this technology translation. How do we do that fast? Instead of traditional academia research, might be policy, might be market, finance, and equity. So the Tomcat Innovation Transfer Program at Stanford within Precourt has been around for more than a decade. Now we spin out about 100 companies. So this all need to be considered when I look at technology from the lab going to the market with scale.